Can you all hear me clearly?
Yes, Dr.
Okay, good. Thank you. Well, first of all, I would like to welcome you all into my lecture, yeah, and also to University of Indonesia as well. Even though at the moment we are still doing the online course, I hope by next week you all can visit UI. Do you mind if I ask you all to open camera first so that I can see your faces? Maybe later when I deliver the course, you don't have to open the camera, and neither do I. We can just focus on the slides. Okay, thank you. Well, I want to get to know each other. Yeah. Well, first of all, I would like to introduce myself. My name is Handhika, Handhika Ramadhan. I am the instructor for today's University of Indonesia Creates class, Advanced Analytical Dynamics. Yeah. So here I have Hasif Adli. Hello, Asif Adli.
Hello, Assalamualaikum.
Waalaikumsalam. Are you from Malaysia?
Yes, I'm from Malaysia.
Okay. So at the moment you are in UM?
No, currently I'm in semester break.
Oh, in semester break. Okay. Okay.
Yes,
So,
I'm at my house.
in your house. Okay. And then I also have Madesh Kumar. Hello. How do I call you, Madesh or Kumar?
Madesh, can call me Madesh.
Madesh. Okay. So
Yeah.
you're also so all of you are UM students.
Yeah.
Okay. Also, I have Chia Ji. Yeah. Sorry if I pronounced correctly. Incorrectly.
Yeah, correct.
So how do I call you, Chia?
Yeah, Chia.
Okay. Thank you. Welcome to my class. Also, I have Iqbal Afif. Hello, Iqbal. I also have Hafiz Amarullah. Hello, Hafiz. Ahmad Marwan.
Yes, sir.
Hi, Ahmad. Well, can you open the camera?
I'm sorry, sir. I
Okay.
cannot go for now.
Okay. Okay. Thank you. Also, I have Nurul. Hello, Nurul.
Hi, sir.
Okay. Is that your only name, or I mean, do you have any?
My name is actually Nurul Izian, but
Nurul
you can
Izan.
call me Nurul.
Okay, thank you, Nurul. Welcome to my class. I also have Tirnisha. Is that correct? Did I pronounce
Yes, sir.
it? Okay, hello, Tirnisha.
Yes, sir.
And also Aiman Hakim. Yeah?
Hello, sir.
Hello. So how many do I get here? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 9 students. Thank you for coming to my class. Maybe this is our first meeting, yeah. So, oh, by the way, do you hear my voice clearly, or is there any delay or lag? Okay. Well, I apologize for my poor English. I don't usually get teaching in English. Well, I do have a class in English once in a week, but yeah. So do not hesitate to correct me if I say wrong things or spell it incorrectly. Okay, so you all are a physics students, yeah, at UM. So is it in which semester are you now, or in what year?
Year 3.
Third year.
Yeah, third year.
Okay.
Most of us, some of us are from second year.
Oh, so it's second and third year, yeah.
Yeah, yes.
Okay. So how is physics in UM? I mean, I don't really know the Department of Physics like in Malaysia or around in Southeast Asia. Like, what have you? Okay, maybe not what have you learned, but do you have like a specialization in there? Like research specialization in your last year, probably like that, or what, something like that.
Doctor, do you mean like final year project or something?
Okay, final project. Okay, and what are the physics? Sorry, the research groups in UM? How many like physics research groups in UM?
Doctor, sorry, I'm not so sure.
Okay, but do you have to join? I mean, you have to join any physics group, like in the last year or something. Or,
no.
No? Okay, so it's optional, yeah.
Yeah.
I see. Okay. Well, as I said, yeah. Okay. I haven't. I haven't graded. There are three more people here, yeah. VJPI. Sorry, may I know your name, sir or miss?
Hello, doctor. It's me. I'm Baxter Joali.
Oh, okay. Sorry. How do you call your name?
My name is Baxter Joali. Just call me Baxter.
Baxter.
Yeah, Baxter.
Baxter. Okay.
Yeah.
Is it possible for you to open your camera first? Just for the introduction.
Yeah, because I'm outside now.
Okay. Okay.
I'm
No
teaching someone.
Okay. No problem.
Sorry, doctor.
It's okay. It's okay.
I will be arriving my home at within 10 minutes, like that.
Okay. No
Yeah.
problem. And you are also a UM student?
Yes, I'm UM student.
Thank you.
Okay,
So yeah, regarding your question, is it like physics community? Well, yeah, I mean, I don't know how you call that in UM, yeah, but like in my campus, so there are research specialization, yeah, for the lecturers, yeah. So some of them specialize in like astrophysics, others specialize in condensed matter physics, and other in material science, and so on and so on. I mean, do you also have that kind of thing in UM? And well, my question was, were you obligated to join? But I think Chia already answered that it's an optional, yeah. Okay. I also see there are three names who look like Indonesian names to me here. They are Muhammad Renaldo Putrayadi. Hello. How do I call you, Renaldo or Muhammad?
Hello, Mr.
Yeah. Are you a UM student or Indonesian student?
I'm a University of Indonesia
Okay,
student.
so you are my student.
Yeah.
Can you open your camera, please? Or is it possible?
Wait, Mr.
Yeah, okay. So in what year are you?
I'm at 7th semester now.
7th semester.
Yeah.
Okay. Also, there is Gavin Setiawan. So most likely Gavin is also a UI student, yeah. Hello, Gavin.
Iya, Pak.
Okay, thank you. I also saw another student, a girl, but I think she was gone. Maybe she will rejoin. Okay, for Ronaldo and Gavin, since this is the international class, I would like to ask your permission to deliver this class in English. Yeah.
Okay.
But if you have any questions and you have any difficulty in asking in English, just drop me a question in Indonesia. I'll try my best to restating it in English and to answer it. Okay, so thank you all for. Oh, there's another one joining. Who's this? There is Muhammad Haras Takif. Hello, Muhammad Haras. How do I call you?
Hello, just call me Haras.
Haras. Okay. Welcome to my class. Are you a UM student?
Yeah, I am a UM student.
Actually, how many students, UM students, do I got?
I think around 15 or 16.
15. Okay. Wow. Okay. While we are waiting for others to come, let us just get along with this, move on with this introduction and go to the course. Yeah. So as you already know, this is a program of like summer courses, yeah, by University of Indonesia. Well, in University of Indonesia, we have actually 5. I mean, in the Department of Physics, University of Indonesia, we have 5 research specializations or research groups. Yeah. First one is theoretical nuclear and particle physics and astrophysics. That's one research group. Also, we have a theoretical condensed matter physics. We have material physics. We have medical and biophysics, medical physics and biophysics. Yeah. And the last one, we have instrumentation physics and control. So yeah, there are 5 groups where each lecturers or professors, yeah, belong to. I myself belong to the theoretical nuclear and particle physics and astrophysics. In particular, my research interest lies in astrophysics, yeah, theoretical astrophysics and cosmology. I've been working on the black hole, yeah, theoretical black hole for the past couple few years. Okay, maybe before I proceed, I can show my oops, sorry. Sorry, let me just open my screen first. All right, so yeah, maybe this is just for the introduction, yeah. So you can get to know me a little bit better, yeah. Well, you can find me in the physics UI website. Let me just share. Can you see it clearly? Okay, so this is me. I graduated from this alma mater, from University of Indonesia, and then I continued my study in US, especially in general relativity and cosmology. You can also find my publications either in Google Scholar or in Scopus from this homepage. Also, I have a YouTube channel to share my lectures, some of my lectures online, and you are welcome to visit my YouTube channel. Let me just open it. Well, but most of my online lectures are delivered in Bahasa Indonesia, but I'm planning to also make some videos and also more videos in English, so that my channel can reach a wider audience. So this is my YouTube channel. You can just search Handhika Ramadhan. I posted some of my online courses, especially during the COVID a few years ago. Still a few, not many, but I'm planning to add more. Okay, so any question about me or about my research or anything related to me before we start? Okay. Okay, so I guess there's no question, so we can proceed. So if you also recall, my topic of this lecture is about advanced analytical dynamics. Well, so first of all, before I deliver my lecture, I would like to know about your background in classical mechanics, or in mechanics. So for the students, have you taken a course in classical mechanics, or is it the same name in UM?
Yes, Dr. We have taken, I think, most of us.
Okay, so how far or how much does it cover?
I think basically we covered the Newton's law of that, and Lagrangian and Hamiltonian dynamics.
So okay, how far in Hamiltonian dynamics?
We are taught to apply the Lagrangian dynamics to solve like problems. That the steps. We are taught
Is that in the second year or in the third year?
the second year.
Okay. Well, thank you, Chia, for the information. So I assume that all of you are familiar with classical dynamics, So I hope my lecture is not too boring because it's also related to that, but maybe I will go dig deeper, we'll see how much deeper we can get, but it's essentially about a classical, advanced classical dynamics, something like that, So I apologize if my course is kind of trivial. Well, I hope I can have some. I give you some alternative view. So the reason is because so in this program, Department of Physics, University of Indonesia decided to divide the slots for this lecture to 5 research group, yeah, evenly, yeah. So each group, each group has 4 weeks, yeah, for to deliver their content, yeah. So from my group, from the theoretical astrophysics group, it's me and Dr. Ar-Rahim. Maybe he will be giving the lecture after me, maybe next week, yeah. So me and Dr. Ar-Rahim. So each of us only has a 2-week slot, yeah, or two meetings, yeah, today and next week for me. And so when I was given this assignment, I kind of think that how can I deliver topic related to my research, specific research topic that I'm working on. If I'm just given a 2 weeks, I think it wouldn't be effective to proceed, yeah. So I decided not to talk about a black hole and its properties, yeah, something. I mean, because it will. I have to discuss many things, yeah, before I can arrive at the dynamics of black hole that I'm working on. So I decided instead to talk about the analytical dynamics, which also I use in the study of black hole, yeah, and also in the study of a many body problems in astrophysics, in orbital dynamics right now. So maybe this a short lecture, even though it's not satisfactory, will be helpful somehow to you. Okay, so yeah, that's my a little background about the topic of my research, yeah. And also, if you have any question, please you can raise your hand here or just talk to me directly. May I know what kind of textbooks you are using in classical mechanics?
We are using Classical Dynamics of Particles and Systems by Thornton and
Okay. So
Yeah.
yeah, by Marion and Thornton. Yeah. So it's the same, yeah, here in Indonesia.
Oh,
So yeah, especially in UI, we use the same textbook. So okay, so I think we can. It's good. I mean, I can get the picture. Okay, so if there is no question, maybe we can start. Yeah. So yeah, my lecture is divided into two meetings. Yeah, one is today, and the other one is next week, if I'm not mistaken. Today's online, and next week is offline. Yeah, so you all come to the Department of Physics UI, and we will meet offline, maybe in a class. Yeah. So actually, when I deliver this, or in most of my classes, if it's offline, I always use whiteboard or blackboard, yeah, and to derive equations. Yeah, I mean that's usually my style. But since today is online, I don't think it's practical if I'm using a online blackboard. So today I'm preparing I have prepared my my presentations. and maybe I can share my presentation after the class. Yeah. But I do hope that next week when we meet offline, I'm planning to give a lecture. One, maybe not using presentation slides, but using whiteboard. Yeah. So yeah. So I will use whiteboard a lot next week. Okay. Well, I think that's so much about it. If there is no question, I can share my screen maybe. Yeah. Oh, okay. What is this? Let me. Okay, sorry, this is loading. First. Where is it? Where is it? I cannot find it. Wait. All right. Can you all see my screen?
Yes, Doctor.
Yes, can Doctor.
Okay. So, yeah, topic of this talk is about advanced analytical dynamics. Yeah, and I once again apologize if the content of my lecture greatly overlap with the course in your UM mechanic class. Yeah, I do hope that there is something new here. Okay, so right, let me just start. So the content of this course is as follows. Yeah, first I would like to talk about some introduction, and by introduction, I mean I'm gonna briefly, very briefly review about Newtonian dynamics. Yeah, and also conservation laws. I'm pretty sure you all have studied this, and also I'm gonna discuss configuration space and constraint, also generalized coordinates. Now I'm going to enter several alternative methods to deriving the equation of motions of a particle or system, yeah, other than Newton's laws. And in this course, the alternative methods that I am going to discuss, yeah, is a principle of least constraint, Gauss principle of least constraint, and also the Udwadiya-Kalaba equations of motion, also principle of virtual work and the D'Alembert principle. Yeah, and the last time is maybe you are already familiar, the Hamilton principle. Okay, if you want to turn off your camera, you may do so. And if you wanna have a question, I cannot see whether you are raising hand or not, so you can just raise your voice, yeah, so that I can hear you. And you don't have to wait for the end of this course to ask question. You can ask question if you find my explanation confusing or something, yeah, or wrong, or you don't find it clear. Okay. There are some sources, and by sources here, some textbooks, yeah, I am using. Leonard Meyerowitz, Methods of Analytical Dynamics. Herbert Goldstein, this is Classical Mechanics. Pars, a Treatise on Analytical Dynamics. Hand and Finch, Analytical Mechanics. And Udua Kalaba, Analytical Dynamics, A New Approach. Oh, by the way, one reason why I'm choosing this topic is also because even though this is more like advanced classical mechanics, it supports also my research, yeah, as I said before. I've been working on the orbital dynamics of black hole on one hand, and also I've been at the moment. I'm also collaborating with some of my colleagues to work on a dynamics of 3 and many body problems, yeah, in astronomy or in astrophysics. So this analytical dynamics method are highly useful for me. Okay, so dynamics always starts with Newtonian. Yeah, you already know this, but I think there is nothing wrong if I'm briefly discussing about this. Right, Newtonian dynamics always starts with a single particle first, and then with a motion of single particle, right? And later we are going to discuss a system of many particles. So the parameter that characterizes the motion is what we call the position vector. And from position vector, we can define the velocity as the first derivative of the position vector with respect to time, and also the momentum. Yeah, and basically Newton's law said that the rate change of momentum of the particle or the system is equivalent to the sum of all forces involved. So the problem in Newtonian dynamics is always that given a system or a particle and the known forces involved, we are asked to solve the position vector, or in other words, we are asked to solve the behavior of particle at any time. So where the particle is at any time and what the velocity is at any time, and so on. Okay. So that's the fundamental problem in mechanics or in dynamics. Yeah, and that's that's why people devise many methods to solve that question. So basically, Newton's law is do you see my cursor, my pointer here?
Yes.
Okay, thank you. So basically, Newton's law is a differential equations. Yeah, you solve differential equations, you get the solution, you get the behavior of the particle. Yeah, and how do you solve the differential equation? Well, by techniques that you learn in the mathematical methods for in physics, yeah, or in UI we call it the Physica Mathematica or mathematical physics. Yeah, like solving differential equations is part of the mathematical physics. Okay, now what if we have more than one particle? We have a number of particles. Let's call there are n number of particles in a system. So I define system as a closed area enclosing a number of particles. So this system of particle can be discrete like this, or it can be continuous. Yeah, like for example in rigid bodies. Yeah, or in a fluid. Yeah. Classically, we can perceive them as continuous. Yeah, even though quantum mechanically there is we cannot divide them less than atom. So atom is the smallest constituent particle. So perceived quantum mechanically, all continuous system is also discrete. But let's talk about classical here. Yeah. So if I have a system of n number of particles, in this illustration, I'm using 5 particles, but you can easily generalize the number of particles to any number. Yeah. There are two forces involved here. In general, yeah, I don't specify what kind of forces, but in general, the forces can always be classified, or can always be partitioned as what we call the external force and the internal force. The external force is the force that is given by from the outside of the system. Yeah. For example, if the system is subjected to gravitational force or a Coulomb force, then the gravitational force or the Coulomb force act like external force. Okay. Besides external force, we also have internal forces. Yeah. And internal forces is defined as the force that acts on each particle with respect to the others. Yeah. So so here the external force is denoted by the F subscript I, yeah, and superscript E. So E, the superscript E denotes the external, and the I here labels the particle. So Fi here labels the external force that the ith particle experiences. For example, if I'm talking about the M1 is a mass of particle 1 here. So the external force that the M1 experiences is F1. Okay. And also we have internal force. Internal force, here we make assumption that in the internal force is mutual. What I mean by mutual is that if I have, so the internal force is denoted by Fij. So I and J label the number of particles, which particle we are talking about. So for example, if we do have internal force between M1 and M2, I'm calling it F12. Okay, so F12 here is defined as the force that the particle 2 experiences due to particle 1. And so since it is mutual, by definition it should be mutual. So the particle 1 also experiences a force, yeah, due to M2, and we call it F21. So the mutuality is defined like this. Yeah, the Fij is minus Fji. And also we make another assumption that the internal force is central. What I mean by central is that the direction is along the vector between between the particle I and the particle j. So Rij is defined as the Ri minus Rj. Ri is the position vector of particle I. Let's take it with respect to some arbitrary origin of reference. It can be inside or it can be outside the system, and Rj subsequently is also the position vector of the part of the jth particle with respect to the origin. So now the Rij is the vector position vector from particle I to particle j. Okay, So we don't really care about the origin, and that's why the absolute value of Ri and Rj are here is not really important. What is important is the difference, the vector, the vectorial difference between Ri and Rj. That's what we call the Rij. So Rij is the position vector between particle ith, the ith particle and the jth particle. For example, R12 is the position vector between M1 and M2. You can as well say that R12 is the position vector that goes from M2 to M1. And so R21 is the position vector that goes from M1 to M2. Okay. So we make these two assumptions for the internal force. Yeah, the internal force is mutual and it's central. By central, what I mean by central is that first it only depends on the radial distance, and second, it the direction of the force is parallel to the direction of the position vector. Okay, now the total force that the ith particle experiences is can be given by this. Yeah, the total Fie. So here I assume that Fie is the total external force that the ith particle experiences. Okay, if you have more than one external force, then you can put all of them here. Yeah, so this is just the total plus the sum of all internal forces that it experiences with respect to other particles. Okay, so if we have n particles, totally m particles in the system S, then the total internal forces that the ith particle experiences is given by the sum of j from 1 to n, yeah, of Fji. But logically, j runs from 1 to n, but it excludes I, right? Because there is no internal force between the ith particle with itself, right? The internal force is only between the ith particle with the rest or the others, not with itself. So I have to exclude the I here. Another way of writing it is by writing it like this, yeah, the summation of j from 1 to n. Just make it arbitrary. You can include j equals I here, but then I put a factor like here, 1 minus delta ij, and delta ij is I'm sure you already know, it's a delta Kronecker. Yeah, the value is 1 if j is equal to I, and 0 when j is not equal to I. Yeah, so the delta Kronecker here excludes the contribution from j equals I automatically. All right, so those are the total force. So we can put it in the Newton's equation. So on the other hand, the what do you call the rate of change of the momentum of the ith momentum is given by this, or equivalently the second derivative with respect to time of mi times ri. Okay. All right. So this is the Newton's equation for for any particle in the system S. So each particle has must satisfy this equation in order to behave accordingly. Okay. So in other words, I can say that the behavior of each particle in the system is governed by this equation, right? So we have n number of equations here in this case, because I runs from 1 to n. So for each I, you have this equation. Okay, so you have 10 particles in a system, you have 10 equations like this. Okay, for each I. Remember the J is run over, yeah. J is run from 1 to n. For each equation, J runs from 1 to n. Okay. Okay. So how about the total forces on the system? This is the total force in one particle. Yeah. How about the total forces on the total system? So if we want to talk about the total system or the system as a whole, I have to sum both sides with respect to I, right? So on the left-hand side, I sum I from 1 to n, and also on the right-hand side, the same. Yeah, I sum I sum I from 1 to n. Now the first term is this one. Yeah, the first term. This is the sum of fi from 1 to n. What does this represent? This represents the sum of all the sum of external forces that each particle experiences. So each particle experiences fi of E. Then I sum for all I. The Fe represents the total external forces working on the system. The second term, the internal force, the summation is 0. Anyone knows why? The summation of this one, if you work it on, is 0, right? The logic, it's simple because due to the mutuality of the internal force. So let's say that M1 has F21 with respect to M2, yeah. M1 has F31 with respect to M3. M1 has F41 with respect to M4, and it has F51 with respect to F5. Yeah, M5, sorry. Okay, that's the internal force that particle 1 experiences. But if you want to sum over all total internal force, so you sum the internal forces that the M1 experiences plus the internal forces that the M2 experiences, and so on. But from M2, we have also F12, which is the minus of F21. So the F12 here cancels F21, okay? And so for M3, we have F13, which cancels F31, etc. So at the end, all the internal forces summation cancel out completely. So you are left with 0. In other words, the total forces on the system does not have any contribution from the internal forces. So looking by the observer from outside the system behaves, the behavior of the system is only governed by the external forces that the system receive, not by the internal forces that the system has. Also, we can define what we call the center of mass coordinate. I call it CM here. CM is defined as like this. I have the capital R. Capital R is the position vector of the CM. It's defined as the summation of MI RI divided by total M. Yeah. So I have this one. So I can have the equation for the mass center of mass. The total mass times the coordinate of the center of mass is the same as the summation of MI RI. Okay. Now, using this expression, I can put it back here. Yeah, I can put it back here. I can. So if you see here, if I open the pi dot is just like this. So I can put the summation of I inside the second derivative. I can have this equation. So I end up with this equation. What does that imply? This implies that under external forces, the system behaves as if all the forces work on the CM. So for the observer outside the system, we don't really care what kind of internal forces are going on inside the system. We don't even care the configuration of external forces working on the system. We can perceive system moving as if the total external forces only work on the CM. So this kind of picture really simplifies how we study the system. Yeah, we just look at the center of mass of the system and the behavior of the system as if the system is reduced to a point, and the point is its center of mass, and all the forces work on that point. Okay, so now what if the external forces is zero? If the external forces is zero, then the right-hand side is zero. The second derivative of r with respect to t is zero, which means that the momentum is constant. So the linear momentum is constant. If there is no external applied force on the system, the external momentum of the system is constant. Yeah. If the system was at rest, then the system will be at rest all the time. If the system was initially moving with a constant velocity, then the system will always be moving with constant velocity all the time. Okay. All right. Now, how about angular momentum? Well, angular momentum can be defined. We know the definition of angular momentum. Yeah, this is the cross product of the position vector and its momentum, linear momentum. So if I'm calculating the total angular momentum, I'm just sum them over for each I get this expression. Right, I get this expression. Now, so the right hand side. So sorry, I have to go back and forth. Yeah, if you see this, or maybe yeah, sorry, maybe this one. Yeah. So I can start from this, and if you a cross product Ri with respect to Pi dot, yeah, and then you sum them over for all of I. So the right hand side, you get this one, right? Now the left hand side, this cross product can be partitioned using the vector identity, vector property, yeah, like this, yeah. So the total derivative of Ri cross Mi yeah, minus Mi times the Ri dot cross Vi. So Ri dot is the derivative of Ri with respect to t, yeah, and Ri dot is just the V. So we have V cross V, and we know V cross V is 0. So the left hand side is just like this. The right hand side stays. So the left hand side, sorry, the left hand side, this is just the Ri cross Mi Vi is just the definition of the angular momentum. Yeah. So this is the rate change of angular momentum with respect to time, the left hand side. The right hand side, on the other hand, yeah, we have to work it out. So the first term on the right hand side, I'm just leave it as it is. This is just the total external torsion, yeah, the total external torque. How about this second term? The second term needs a more elaboration. Here I elaborated here. So if you work it out, this can be written as Ri cross Fji plus Rj cross Fij. Sorry, Ri cross Fji, yeah, plus Rj cross Fij. So this is proportional. Yeah. So this operation is proportional to this expression, right? So now I can use the definition of Rij, yeah, which is Ri minus Rj. And since we know that the cross product is anti-symmetric, the right hand side can be written like this way. Okay, and this is just the definition of Rij. So at the end we have this operation is proportional to the Rij cross Fji. Now, if you remember, we assume that the internal force is mutual and central. Yeah, central means that Fji, its direction is along the Rji, which means that this cross product is zero, right? Because it is as if you are crossing, you're doing the cross product of Rij with itself, right? So this is zero, which means that the second term is once again zero for this operation. So we are left with this equation. As I said, the left-hand side is just dl dt, and the right-hand side is the total torque. I call it N. So this is just the expression for, or the equation for angular momentum. So if the total external torque is zero, then the angular momentum of the system is conserved. Yeah. So the conservation of the angular momentum of the system is determined solely by the external torque applied on the system, not on the internal forces. All right. Last time about this Newtonian dynamics, about the energy of the system. Yeah, the energy, or the work, to be precise, is defined to be the integral of Fi dot dri. Yeah, so this is the work. The force done along a displacement. Right. Now, this is the work done for each particle. So if you want to know the work of the system, then I sum them over for all I. Okay. Now, since F can be partitioned into the external and internal forces, so the integral can be written like this. Yeah, this is for the external force, the first term. The second term for the internal forces. Well, you know, you are familiar that this integral, yeah, can just be written, the left-hand side, I mean, can just be written as the change of kinetic energy. Okay. Now we just need to work out the right-hand side. The right-hand side, I make additional assumptions here that the forces involved, either the external or the internal forces, I assume that they are all conservative. And by conservative, I mean that the force can be written as the minus gradient of some potential energy. Yeah, the Vi is the potential energy of the ith particle. So this is scalar. The V is scalar. T is scalar. Yeah. Since it's conservative, it can be expressed that way. So the integral can be done this way. I'm sorry, I haven't put the boundary here. I forgot to put the boundary. So putting the boundary, you get that the integral gives you Vi1 minus Vi2. Okay. Yeah, for the internal force, as I said, I assume also that it's a conservative. Yeah. Sorry, I have a typo again here. It should be minus gradient. Yeah. So please apologize. I will send you the revised or the corrected slides after the talk. Yeah. So this should be minus gradient of Vij. Yeah. So Vij is the potential energy between the ith and the jth particles. Yeah. And it is proportional to the scalar distance between them. Okay. So if I integrate the internal force with respect to the displacement, I can write down this dot product as this way. Yeah. Okay. Since the product is symmetric, so I can write down this, and I put half here to avoid overcounting. So, well, this is just the Fij dot d of Rij. Okay. And since this is conservative, the integral also give you just the potential difference. So the total potential you get from the external and internal forces are given by this one. This is the total external, the total external potential energy. This is the total internal potential energy. So this is the total potential, yeah, the V total. So putting them all together, we arrive at the familiar energy conservation, yeah. That the T1 plus V total V1 is equal to T2 plus total V2, or in other words, T plus V is constant, and the constant can be defined as the total energy. So if that says that if the system is conservative, if the system receives conservative force, yeah, and if the system is time independent, then the total energy is conserved. This is just the conservation energy for the system. Okay, so I think that's so much about the Newtonian dynamics. Yeah, I'm going to talk about configuration space here, since we are talking about a system of particle. So imagine that this is a system of particle, yeah, that I was talking about. There are n objects. So this system of particle, as it evolves in time, it defines what we call the 3n dimensional configuration space. Yeah. So the configuration space is the space of all positions of the corresponding particles in a system. So since we are talking about 3 dimensions, so for n object we have 3n dimensional configuration space. Yeah. Okay. So Mi is the mass of each particle. This labels the mass of each particle, so M1, M2, up to Mn. Yeah. And so Ri, this is what I call the configuration space or configuration vector. Yeah. Ri, this is a 3n vector matrix. Yeah. It contains x1, y1, z1. This is the 3-dimensional coordinate for particle 1, x2, y2, z2, the 3-dimensional coordinate for particle 2, and so on until xn, yn, zn. Yeah, this is the 3-dimensional coordinate for the nth particle. So the configuration vector space can be written like this. So this T means that this is a transpose. Yeah. So this is a vector. In matrix, this is a vector. Okay, this is what we call the configuration space. I'm going to use the configuration space later, yeah, today and maybe next week. I'm going to talk about constraint. What is constraint? So basically what I've been talking can be summarized as follows. Yeah. Given all the forces known, yeah, given all the external forces known, and if we are given the information of the internal forces, basically we can use this Newton's equation to solve the behavior of the system, right? Or can we? The question is like that. Yeah. So the basic premise of Newton's equation is that put all the forces you know here and here, you can solve this differential equation to get the Ri, or to get the position vector as a function of time for each particle, right? That's the basic premise of Newton's equations. But it turns out that these equations alone, by the way, this is a, you have n number of equations here, right? Because I runs from 1 to n. So you have to solve n number of equations consistently and simultaneously, right? Because this n number of equations are most likely be coupled to each other. Now, in most cases, this complication even is not enough to give us the solution for the system. Yeah. In other words, this is insufficient. This mere equation is insufficient for us to solve the position vector, yeah, or the behavior. Yeah. Most systems, if not all, yeah, they are subjected to a constraint or more than one constraint. Sorry, I made a typo here. Should be constraints. Made a typo here. I'll correct it later. Okay, so knowing the equation, the Newton's equation itself, is not enough. You have also to know the constraints imposed on the system. So what is constraint actually? Constraint is a condition or conditions that a system must satisfy in its every dynamics. So if you observe that every dynamics, all of them, I can say almost all of them, if not all, yeah, they satisfy some constraints, right? They satisfy some constraints. Okay. Even some system which look like a free particle, somehow there must be some constraint imposed on them. Okay, what's the example? Let's take a simple example. I have a particle of mass m sliding on a smooth ram. Yeah, this is a ram. And the ram makes a angle alpha with respect to the ground. So this is the particle. Let's assume that the particle is a point particle, so we don't care about the shape and the geometry. Yeah, it only has mass m. It's a point particle. So if you use Newton's equation, you will end up with these a set of equations, these two equations. Yeah, n is the normal force, mg is the weight. Yeah, alpha is the angle of the ram. Yeah, x and y is the horizontal and the vertical position of the system for each time. Okay, this is simple. This is from basic physics. I'm just using it to illustrate my case. Okay. But if you can see, there is a problem here. What is the problem? The problem is that we are given two equations, but we have to solve for three unknown functions. What are the three unknown functions? We have to solve x, we have to solve y, and we have to solve n. Right? These are three quantities that we have to solve. But we are only given two equations. Then how do we solve them? So two equations to solve for three unknown functions. This is the condition for what we call the undetermined system. Yeah, undetermined system. Yeah, you cannot have a unique solution, because to have a unique solution, the number of the equation must match the number of unknown quantities. Yeah, so if you want to solve for three unknown quantities, then you at least you have to have three equations, but now you only have two. How do we solve this problem? Well, this is what happens if you only look at the Newton's equation. In fact, the system is constrained. There is a constraint imposed on the system, and once we know the constraint, we can simplify the problem. What is the constraint of the system? The constraint is that the motion is possible only on the ram, only on the inclined plane. So here, even though we are looking for the x and y as a function of time, the x is the horizontal, y is the vertical positions. Yeah, But you see, the system doesn't have freedom to move in X and Y simultaneously, right? It doesn't have freedom in X and Y. Why? Why? Because it is working. It is sliding, or it is moving on an inclined plane, and the inclined plane, and this is the constraint. In this inclined plane, it restricts the freedom of X and Y. You cannot both have free X and free Y. If you fix X, then Y is no longer free. In other words, the constraint can be written as like this. This is the constraint that the system obeys, that the Y over X is tangent alpha. So this is the third equation that we need to solve for the system. So now we have 3 equations for 3 unknown functions. Let's solve. So using that, we can, using this constraint, we can differentiate twice with respect to time, and we can insert it to one of the 2 equations before. And here, this is the only equation that we need to solve, right? So integrating it twice, you know the X as a function of time. Once you know X as a function of time, you can solve for Y as a function of time. And also you can get the N, right? The normal force. So this is how the constraint, the knowledge of a constraint helps us in solving problems. What kind of system that? What kind of system? What kind of constraint that we can find? Well, there are many systems that has constraint. For example, we have a bead on a rotating ring. So what is the constraint here? The constraint is that the motion of the bead can only be along the ring, right? So this constraint restricts the freedom of X and Y. So X and Y are no longer free coordinates, but they are constrained by this equation, where capital R is the radius of the ring. You can also have even a simple system like a ball bouncing on the ground. Yeah, you have a ball bouncing on the ground. This is constrained. Yeah. What is the constraint? The constraint is that the ball can only move above the ground. Above the ground. So if Y here denotes the vertical coordinates and X and Z are the ground, yeah, then the ball is constrained to move only along Y is greater or equals 0. You cannot have the ball moving for Y less than 0, right? You cannot have the ball moving underground for this system. Yeah. So this is the system for this simple system. This is the constraint for this simple system. Another constraint we can find is the gas molecules in a chamber. Well, the chamber itself is a constraint. Yeah. So if you have n number of gas molecules, each can go randomly and arbitrarily. Yeah, but they can only move inside the chamber. So the walls of the chamber work as a constraint. Yeah. So in other words, if Ri denotes the position vector of each particle, yeah, I runs from 1 to n. Yeah. So there are n number of particles. So Ri are constrained like this. Yeah. So Xi is constrained from 0 to the width of the wall. Yeah. Yi is constrained from 0 to the length of the wall. Yeah. And Zi is constrained from 0 to the height of the wall. Okay. So this is another example of a constraint system. All right. So knowing constraint, we can classify constraint into several classifications. First, we can classify constraint into holonomic and non-holonomic. I will explain later what is holonomic and non-holonomic. Yeah. Also, we can classify constraint into scleronomous, and by scleronomous I mean time independent. So the constraint doesn't depend on time. The equation for the constraint doesn't depend on time, and the constraint can also be rheonomous or time dependent. The equation for the constraint is includes time. Okay. Okay. What is holonomic and what is non-holonomic? So holonomic constraint means that you can always write down the equation for constraint in this form. This is the most general form for holonomic constraint. Okay, so if we look back to the previous previous illustration, we can see that the particle sliding on a smooth ramp, it has holonomic constraint, right? Because now I can write down y is x times tangent alpha, or y minus x tangent alpha is equal to 0, right? This is a holonomic constraint. This is also holonomic constraint, right? Because I can write down x squared plus y squared minus r squared equals 0. But this one is non-holonomic because the constraint is expressed in terms of inequality, not equality. So this inequality is what it falls into the holonomic classification, non-holonomic classification, I mean. And so is gas molecules in the chamber, the constraint is non-holonomic because these are inequalities. Okay. So holonomic constraint, first, it must be expressed in terms of equality. Yeah. So all holonomic constraint is an equality, but the reverse is not necessarily true. Yeah. If the holonomic constraint is equality, it doesn't mean that the non-holonomic constraint must always be inequality. No. The non-holonomic constraint can be expressed as an equality as well as an inequality. Yeah. But the holonomic constraint must always be in an equality form like this. Now, you can also express this in terms of what we call the Pfaffian form. Yeah, the Pfaffian. Pfaffian is a term based on if I'm not mistaken, a German mathematician, either German or other European country, I forgot. Pfaff, yeah. His name is Pfaff, so it's called Pfaffian. In other words, the holonomic constraint can also be found in this type of equation. Yeah. So if you find equation of constraint in terms of a differential like this, it doesn't necessarily mean that this type is non-holonomic. No. This can be written. This can be classified as holonomic constraint, but written in Pfaffian form. So, what is the requirement that this expression be holonomic? Well, the expression is that this equation must be the total differential form of that equation. Okay, so if I take the total differential of this equation, then it should get that equation. In other words, the vector A of I must be written as the gradient of f here, and the scalar b must be expressed as the partial derivative of f with respect to t. Okay. So if you put the definition of A, I, and B here, you can see that this Pfaffian form can just be written like this. And we can, once we get this, you can integrate this. So the right-hand side will be constant. You can pull the constant of integration to the left-hand side, and we once again get this expression. So in other words, the holonomic constraint can be perfectly expressed in terms of Pfaffian with the requirement that the AI and the B functions given by this, right? So that the Pfaffian form can be expressed as the total differential of the algebraic holonomic form. Now, there are several nomenclature here. If the function of the vector of AI is not a function of time, and B is 0, which means that none of the function in the holonomic condition is a function of time, then the constraint is scleronomous, right? Otherwise, the constraint is rheonomous. So holonomic constraint can be scleronomous as well as rheonomous. And for the scleronomous constraint, and for the holonomic constraint, if B is 0, so there is no this term, right? There is no function that multiplies dt, then the constraint is called catastatic. So catastatic holonomic or catastatic non-holonomic, yeah, constraint. So these are just some nomenclatures, some definitions. Okay, so far any question, or I can just proceed. All right, so as I said, I can have more than one constraints. So for general, the equation for a constraint can be written like this: J run from 1 to H. H is the total number of constraints. So I run from 1 to 3n. 3n is the dimension of the configuration space. J is the dimension of H is the dimension of the constraint or the number of constraint. Okay, so please don't get confused. So if I have H number of constraint, then the Pfaffian form of the holonomic constraint can be written like this, yeah, in terms of the what do you call the index, yeah, the dummy index, the dummy indices. I wrote it JI, yeah. AJI is the partial Fj, partial Xi, okay. And Bj is a partial Fj of partial T. Okay. Now, if I divide, or if I differentiate both sides with dt with respect to dt, then the equation for the general holonomic constraint can be written like this. Okay. So this is xi dot. Xi dot is the derivative of xi with respect to t. Okay. All right. How about non-holonomic constraint? Well, non-holonomic constraint simply is constraints, a constraint that cannot be put in this form. Okay. In this form or in its total derivative, total differential form. Yeah, either one. Now, as I said, non-holonomic can be expressed as equality or or inequality. Yeah. The inequality is like the ball bouncing on the floor, on the ground like that, or the molecule in the gas chamber. The equality, you can have it in the Pfaffian, but non-integrable. So this is the inequality example, yeah. While the equality, but non-integrable, you can have this Pfaffian form, okay. But you cannot change. You cannot integrate it, or you cannot express it as a total differential. So yeah. In other words, it is non-integrable. So the Pfaffian takes exactly the same form, yeah. But the problem is now that you cannot express it as a. Sorry, I'm also made mistake. This doesn't work, yeah. This doesn't work because this is the requirement for the holonomic. So I'll delete it. Okay, so yeah, in other words, we have non-holonomic, non-integrable equality constraint like this, but this cannot be brought into the total derivative or non-integrable. What is an example of non-integrable non-holonomic constraint? For example, it's a disk rolling on a horizontal plane. Okay, if you have a disk rolling on a horizontal plane, let's take the illustration like this. This is the X, Y, Z is pointing out in the vertical direction. This is a coin, let's say a disk, yeah. If it's rolling on a ground, yeah, on a floor, since it rolls, then we have the phi dot as angular velocity of this rolling. Okay, so the tangential velocity is given by a times phi dot, and a is the radius of this coin. Now, in general, a rolling coin or a rolling disk like this is parameterized by phi, yeah, the angular, the rolling angular, and by theta. Theta is the position or the angle of the position of this coin on the XY plane, yeah, and by X and Y, okay, X and Y. So these are these four parameters completely characterizes the position of this disk at any time. Okay, now from this configuration, you can easily see that the X dot is just V times sine theta, and Y dot is just minus V times cosine theta. Okay. Now these two, and inserting this expression, can be written as like this. Now you see that this serves as the constraint, as constraint equations. Yeah. Dx minus a sine theta d phi is equal to 0, and dy plus a cosine theta d phi is equal to 0. But you can never express these two equations as a total differential. Yeah, because you can always have arbitrary theta, and it is not related to how many numbers it has rolling. It has rolled. Yeah. So there is no in simplicity, there is no relation between theta and phi. So you cannot express, you can never integrate, you cannot never express this as a total differential. So this is an example of a non-holonomic constraint. And if you meet non-holonomic constraint, the constraint cannot be used to simplify the problem. Then you have to solve the equation of motions along with the equation of constraints simultaneously. So the non-holonomic system is more difficult to solve than the holonomic system. All right, so if we look closer, we can see what is the cause of constraint actually. Why do systems have constraint? Well, constraints actually exist due to the what we call the forces of constraint, or the force or the forces of constraint. See, for example, this particle is sliding down the ramp because there is a force of constraint. In this case, the force of constraint is given by the normal force, right? So the existence of normal force implies that there is a constraint, or the other way around. Yeah, the constraint implies the existence of normal force. So this N is what we call the force of constraint. As well, this as well, yeah, is a particle sliding down a sphere or a hemisphere. You can also look back to previous examples like this. Yeah, the constraint is given by the normal force from the ground. The constraint is given by the force that the wall exerts on the particle when the particle hits the wall, due to the Newton's third law, the wall gives the reaction force. So it serves as a constraint. What else? And this one also, yeah. The ground exerts a normal force on the ball so that it serves as a constraint, etc. Yeah. So we can perceive a constraint as something that is given by due to the existence of some force, and that force is what we call the force of constraint. Now, the force of constraint is denoted by the subscript C here to distinguish it from the external forces, which is not a constraint force. Okay. Now, if we observe, in many cases, the constraint force, it does no work. Yeah, the constraint force does no work. It doesn't do work on the system. What do you mean? What do I mean by that? See, look at this sliding down the ramp. The displacement is along this inclined plane. Okay, I call it dr, and also is dr. And the constraint force is normal force. You see that the normal force dot with dr is 0 because they are orthogonal. And so if I integrate this, this is 0, yeah, which means the integration of n dot dr is the work done by the constraint force. So the constraint force doesn't do any work on the system. You can also see this. We have a dumbbell, yeah, a dumbbell of two masses, yeah, m1 and m2. And the dumbbell is constrained to have a fixed constant distance from each other. Let's call the constant distance L. So why is it constrained to be so? Because we have a force, right? A force that works mutual. So the constraint force is given by this F12 and F21. We can perceive it as some kind of internal force between these two particles. So F12 and F21 are central. In other words, they are proportional to R12, right? R12 is just the position vector of M1 with respect to M2, and the other way around. Now, what is the constraint here? The constraint is that the distance is constant. Yeah, the delta x squared plus delta y squared is equal to L squared, which is constant. So if we know that this is the holonomic constraint. We can identify this as a holonomic constraint. If I take the total differential for both sides, d of R12 squared is just 2 times R12 dot dr12. Yeah, the right hand side is 0 because L is constant. So I have this condition. Now, since the force of constraint is central, is proportional to R12, then if I'm doing dot product of Fij with drij, due to this expression, I get 0. So once again, in this dumbbell system, I can see that the force, the constraint force doesn't do any work. Okay, so if the constraint the constraint force doesn't do any work, then I can put it this way. Yeah, I can dot product the force with ri dot. Yeah, delta ri dot. Delta ri dot is the velocity or it's called the virtual, but I haven't gotten into it yet, but I'm going to discuss about the virtual displacement next week, maybe. Yeah, but let's call it some kind of variation of velocity. Yeah. So if I'm dot producting the force with the variation with some variation of the velocity, I'm doing this one as well. Yeah. But since the constraint doesn't do any work, so this can be dropped. Yeah, this is 0. So I am left with this one. So this is an equation that is important both for today and next week. Okay. Well, you can easily see that this equation implies Newton's law. Yeah, because what is in the parenthesis is simply the Newton's law. Mi r I double dot minus Fi is just Newton's law for the ith particle. Okay. So basically, this is this gives us back Newton's law, but I'm going to use it to go into the Gauss principle of least constraint. Maybe you've heard about the principle of least action, yeah, in classical mechanics, yeah, or Fermat's principle of least time, yeah. Those are a variation of what we call the variational principles. Yeah. Now, this principle was proposed by Carl Friedrich Gauss. I'm sure you all know who Gauss is. He was one of the prominent mathematicians from the 18th century. He made many contributions in geometry and physics. Yeah. Now, well, Gauss' principle of least constraint is an alternative to deriving a equation of motions or Newton's equations, actually. So the equation, the principles says like this. If you have a mechanical system of n particles, sorry, it should be small n, yeah. Let's say, like before, yeah, we have a system of n particles, yeah, and they are moving, mechanic. They are not static, yeah, they are moving. Now, a Gauss principle states that among all the accelerations the system can have at time t, yeah, at any time t, which are compatible with the constraints, the ones that nature picks, or the one that actually happens, yeah, are those which minimizes the following function. The function is what we call the Gaussian function, yeah, or the Gaussian scalar function. And the Gaussian scalar function is written like this. It's defined as a half of sum of I of mi times the square of ri double dot minus fi over mi. Okay, so this is what Gauss defined as the Gaussian or the scalar function. Yeah, we call it Gaussian scalar function. So basically, Gauss' principle says that consider a system of n particles, and if we are given all the constraints imposed on the system, then and also all the forces imposed exerted on the system, then the behavior of the system or the acceleration here is given by the ri double dot, yeah, the acceleration of the system or the acceleration of the any particle on the system is given by the ones that minimizing this function. So basically, this is like solving the least square. Yeah. So this is like a least square. You have a square function. You want to find the solution, yeah, or in this case the ri double dot that minimizes or that makes this square least, yeah, or the minimizing the square function. So that's basically the premise of Gauss' principle. So what is the proof of this one? How can we prove that Gauss' principle actually works? Yeah. Well, when I said how do we prove Gauss' principle, that means that is the same as asking how do we prove that the only acceleration that minimizes the function g is the Ri double dot. Well, we wish to show that if we vary the Ri double dot, or in other words, if I vary the acceleration, then the variation of acceleration actually makes the Gaussian function greater than the original Gaussian function. So by showing that, I can prove that the only minimum value of Gaussian function is when the acceleration takes this form. That's how that's the roadmap. So let's do it. Consider a variation in acceleration. So this is acceleration. We vary it as Ri prime double dot. Yeah, prime here is just the varied acceleration. It is defined as the Ri double dot plus delta Ri double dot. Okay. Now, the corresponding Gaussian function for this varied acceleration is g prime. So in g prime, the only different from the g not unprime is this one. We have the Ri prime double dot. Now let's put the expression of Ri prime double dot here. So Ri prime double dot, if you square it, yeah, you can easily do it. Yeah. Oh, sorry, I made a mistake again. So this shouldn't be prime. Yeah? This should be unprime. Okay, I'll check. I'll correct it again. So the idea is that I want to look for the discrepancy. I want to look for the difference between g prime and g. So delta g is defined as the g prime minus g. Okay, so this is the g prime. This is the g. So this shouldn't have a prime. Yeah, I apologize. I'll correct it. So if you do the calculation is simple, yeah, you can get these two. You are left with these two terms, yeah. So the delta g is half of sum mi delta Ri double dot squared plus mi Ri double dot minus fi delta Ri dot. Okay. Now, we know that the last term is 0 due to this expression, right? So this last term is 0 due to the constraint equation. And the first term, since m must be positive and the square must be positive, yeah, then it is positive definite or positive semi-definite. Yeah, this is always greater or at least equal to 0. In other words, delta g is always greater or equal to 0. Oh, 0. Yeah, delta g is never negative, and this is delta g is 0 if and only if delta Ri double dot is 0. What does that mean? It means that as long as you have a variation in acceleration, then g is always g prime is always greater than g. So the only global minimum of Gaussian scalar function is when you have Ri double dot as the true acceleration. So in this case, we prove that Gauss principle is correct. Yeah. So now, once it is correct, how can we see it? How can we use it? So this is an example, a simple example. This is an Atwood machine. Yeah, Atwood machine is basically a pulley. Yeah, you have two masses hanging on the pulley. One is called mass B with it has capital M. The mass is capital M. The other one is A. It has a small m. Yeah. Suppose that capital M is greater than small m, then we know that the direction of the acceleration, yeah. For capital M, it accelerates downward. For small m, it accelerates upward. Yeah. So how do we calculate the Gauss principle here, or Gaussian function? Well, the Gaussian function for all the systems, since we have two particles, we just sum them up. So we have half. The first mass is capital M. So this R double dot minus what is the force per mass here? Well, the force per mass here is just the gravitational acceleration. Yeah. So G, and here, well, I'm taking the downward direction as positive. Yeah. So this is positive, and here, since small m is moving upward, so it goes in a negative direction. So this is negative. So the Gaussian function for this Atwood machine is like this. So we want to know what is the acceleration of the system. We know how to calculate it using Newton's law, obviously, yeah. But let's use it. Let's use Gauss principle this time. The Gauss principle says that the true acceleration of the system is the one that minimizes G. So how do we minimize G? We know we can just take the derivative with respect to R double dot. Yeah. In other words, we take the variation here. The delta G over delta R double dot is given by this one. Okay, it's given by that one. Now, Gauss principle says that delta G must be 0. Yeah. In other words, we set this whole thing to be 0. So the whole parenthesis is 0. By simple algebra, you can express that the R double dot, or the acceleration of the system, is given by the capital M minus M, small m, divided by capital M plus M times G. And this is exactly the result you can get using Newton's law. Yeah. But this time, we are using a alternative and more advanced principle of least constraint. So in this case, we can perceive that the Newton's law, or Newton's equation, is a consequence of principle of least constraint. It is as if nature always picks a behavior that minimizes the constraint. Yeah. Or in other words, nature behaves as if it tries to what do you call this? Nature behaves in such a way that it avoids constraint as much as possible. Yeah, we can say that way. So using Gauss principle, Newton's laws can have a new meaning, yeah, an alternative meaning. Okay, any question? Sorry. Okay, so if there is no question, I can move on to the development of dynamics based on Gauss principle, and this is what we call the Udwadia-Kalaba theory, or Udwadia-Kalaba fundamental equations. So this is relatively recent development. Yeah, this was developed by Firdaus Udwadia and Robert Kalaba. Both are professors in University of, I forget, Southern California or California, San Diego. Yeah. And these are based on their papers. Yeah, their seminal papers, their classic papers in 1992 and in 2002. Yeah, a new perspective on constraint motion. Actually, I put the I'll share you the slides, and you can click this title, and you will get you can go to the paper. Yeah, I attach the link of the paper here on each title. the link to the corresponding journal, the Proceeding of Royal Society London and the International Journal of Nonlinear Mechanics. So both are actually a professor in mechanical and aeronautical engineering. So this type of equations or this type of approach, the Udwadiya-Kalaba fundamental equations, this is based on a Gauss principle, and this is used widely in the study of robotics and many rigid body problems, and robotics, and also in dynamics and controls. So it has practical applications. So the idea is as follows. Yes, we still have this consider the same system as in the Gauss principle. Suppose that the total imposed force is Fi. Now, since the vector, the configuration space vector is given by this one, so the Newton's law, the Newton's equation is given by this one. Obviously, this is a matrix equations. Since we have n number of particles, so we have the dimension of this matrix is 3n. So M here is the diagonal of M1, 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 M2, 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 M3, 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 up to Mn, Mn, Mn. So here, the dimension of the matrix M is 3n times 3n, okay? And also A is the vector matrix of acceleration. So this is the transpose of A1 T is the transpose of the vector A1. This is the transpose vector A2, etc. until AN. And so is F. So this is a matrix equation in general, because we have n number of particles. And this is unconstrained. We haven't included any constraint here. Now we include the constraint. Suppose this constraint is given as follows. So this is equality constraint. And notice here that the constraint not necessarily holonomic. This can be non-holonomic constraint. So this approach is suitable for non-holonomic constraint, but still in equality form. So the non-holonomic, non-integrable constraint. So if I'm taking the derivative with respect to time for both sides, I have this expression, this long expression. Now this expression can be written in terms of matrix form. In general, I can write down like this. So A is a H times 3n matrix. B is an H vector. So it's a vector matrix with H column. With H rows. One column, H rows. This is H column, H rows, 3n columns. You see that this is more general than this. Okay. So in general, we can write down that the constraint equation is like this. Okay. Now, as we learned before, with the constraints, the acceleration will not be the same as the true acceleration. There will be some deviation from the acceleration if there is no constraint. Now let's call the acceleration after the constraint given by R double dot. And this is actually the one that we are looking for. So if I'm going back here, A is the acceleration of the system if there is no constraint. So this is the unconstrained Newton's law. After the constraint, A is modified into R double dot. Okay. Now we can write down the Gaussian scalar function as follows. Yeah, this is the same Gaussian scalar function, but now it is in terms of the matrix. Yeah, because R, A, and M are matrix. R double dot A and M are matrices. So we have to express them in terms of matrix. So in terms of matrix, we can write down like this or like this. So I'm just splitting the M here, M to the half here and the other M to the half there. So this is just the same here. Now the claim of Udwadia and Kalaba is that for each instant of time, the actual acceleration is given by this solution. So Udwadia and Kalaba proposes that the general solution of the acceleration is given by this. This is the expression for acceleration that minimizes this scalar function. And how do we see that? Okay, I only have 5 minutes, so I hope this I have enough time. Yeah. Now, wait. Okay, before I proceed, you see here there is a peculiar notation. I have plus here. This is not dagger. This is different from dagger. This is plus. What is plus here? Plus here is what we call the Moore-Penrose inverse. So if H is an M times M by N matrix, then H plus is the generalized inverse. Why is it generalized? Well, because we know that for a matrix to have an inverse, it should be squared, yeah, and the matrix should be non-singular. Okay, so that's the requirement that a matrix can have an inverse. Now this is the Moore-Penrose inverse matrix in linear algebra. This is a generalization of the inverse matrix. So a Moore inverse matrix doesn't require the original matrix to be non-singular or square. Okay, so this is, we can say this is a more generalized inverse matrix. So H plus is defined to have the following properties. Yeah, H times H plus times H gives you H. H plus times H plus gives you H plus. Yeah, H times H plus is equal to the transpose of H times H. Sorry, this I mean once again I made a mistake. This should be H plus. Sorry, and H plus times H is the same as the H plus transpose of H plus times H. Okay, so these are some properties of the Moore-Penrose inverse. This is the inverse that I'm using here. Yeah. So this plus sign is the Moore inverse matrix of this A times M minus M to the minus half. So this is the claim. We want to prove the claim. Yeah. First, the proof is twofold. First, we need to show that the solution satisfies the constraint. Okay, this is fairly technical. Maybe you can. I mean, I don't. I'm not sure I can be of any help if I'm explaining it orally like this. But I mean, I can share I will share the slides so you can prove it yourself. So this is the constraint. Yeah. And I can write down the constraint like this. Y, capital Y is some definition. It's like this, yeah. Now, from the MP inverse matrix, if I have a general M and N matrices and X a vector, so this equation is consistent. It's consistent if and only if this condition holds. Okay, so this is consistent if this condition holds. Now that means if this is to be consistent, then this condition must hold. Okay, now let's insert the ansatz, the ansatz into the constraint. Okay, so here we have m double prime. We insert r double prime. I mean, we insert r double prime here. So it's kind of long. So I put b on the left hand side. So the right hand side becomes this one, a times r double prime. So this is r double prime inserted multiplied by a. I get this one. So if I am elaborating this algebra, yeah, I get quite long like this. All right. So the term here can be written down like this, and this term on the in return you can see by the consistency of more Penrose matrix must satisfy this one. So this cancels. Yeah, this cancels. So if this cancels, so we have b. The first term, the first term on the right hand side is 0. So we have b equals this thing, right? B equals this thing, and this is the condition for consistency. Okay, what do we prove here? We prove that the answer satisfies the constraint. Okay. The second proof, we need to show that the ansatz minimizes the Gaussian function. So once again, we do some variation here. We insert the variation, and we know that the condition, the constraint satisfies this. So the condition for the variation is that it must satisfy that one. Now, in general, for the more Penrose inverse matrix, if I have a arbitrary matrix H and arbitrary vector U, then this condition hold. Yeah. So this condition can be written like that. Yeah. Now I'm putting I'm calculating the Gaussian scalar function for the variation. This is like this. Okay, this is kind of long, yeah. In general, I write down like this. So I can simplify something transpose times that thing. Okay. So if I'm working out the this operation, I got 4 terms actually on the right hand side. The first term can be identified as the original Gaussian function, if you can see the previous one. Yeah, this is the Gaussian original function. The second and third term is 0. Why? From the more Penrose matrix inverse. Yeah, and the last term is non-zero, but it's positive. And so we have this relation that the G R prime double dot is equal to G R double dot plus something which is greater or is equal to 0. In other words, G R prime double dot is always greater or equal than G of R double dot. And the equality holds if and only if the variation of R double prime is 0. And by this, I complete the second proof. So here I prove that the ansatz, this ansatz is the one that satisfies the Gauss principle of least constraint. And so the claim of Udwadia Kalabab is proven, yeah, that this is the true acceleration of the system, yeah, the dynamical system, subject to holonomic or non-holonomic constraint is given by this. Okay, I think it's already 10:04. I'm out of time. I can stop my first lecture here. I can continue. I will continue next week. Any question so far?
Doctor, can I ask regarding the dumbbell slide?
Okay, let me just go back to dumbbell. Yeah.
Yeah.
This one?
Yeah, about this, I want to ask, for example, if we use the charges of this particle become a charge, Q1 and Q2, so which means the Coulomb force is the constraint itself?
Well, it depends. I mean, I no, because the Coulomb, because the Coulomb, well, I mean, if the system only consists of these two particles bound by Coulomb force, then the Coulomb force will make the particle either drift apart or attracted to each other, right? So in that example, then this is not a dumbbell model, because this constraint is not satisfied, right? The distance is not constant.
Oh, I see, Doctor.
Yeah, I mean, but you can perceive it like a molecule, like two molecules with a molecules. They are bound by so that their distance is constant, right? So in that molecular system, obviously the physics involved is much more complicated, but from phenomenology we can say that this the system of dimolecule like that resembles the dumbbell system. Yeah. So yeah, this constraint holds. Yeah. But if you have only two fundamental particles, I mean, they are interacting with only Coulomb force. I don't see how they can be constant. Yeah, they will either drift apart or they will be attracted.
Okay, thank you, Doctor. And one more, is there any system that is truly or for real to be unconstrained?
Sorry? Oh, okay. Is there any unconstrained system? Yeah, that's actually a good question. I mean, I think it's relative. Yeah. I mean, even for a free particle, let's say a free particle moving in three-dimensional space. Yeah. For example, you have free particle moving in three-dimensional space, not bound by any potential. From three-dimensional point of view, this is unconstrained system, right? But I can always imagine that well, the free particle is constrained in the sense that it cannot move to the fourth dimension. So the free particle in that sense is constrained, only move in 3 dimension. Yeah, you understand what I'm saying? So
yes.
particle,
So for higher dimension.
yeah, in 3-dimensional we perceive it as unconstrained, but maybe for 4-dimensional observer, it is a constrained system. So I think it's relative. I'm not sure if we really do have an absolute unconstrained system. Yeah.
Yeah, that's an interesting answer from you. Thank you,
Right.
Doctor.
Right. But that's a good question. So I'll look at it. Okay. Any other question? All right. So if you do have a question, you can ask me next week. Yeah, we'll continue about the generalized coordinates and D'Alembert up to D'Alembert principle next week. Okay. Well, if there's no question, I think we can stop here. Thank you very much for your attendance. Let me just stop sharing. And I'll share the slides later. Okay, thank you for coming. We'll see you again next week offline. Okay. So have a good morning. Assalamualaikum.
Thank you, Doctor.
Thank you, Doctor.
Salam.
Bye.